It's late in the afternoon, or maybe it's 9 o'clock at night. You're in a place that's supposed to be for productivity, or maybe for rest, a modern airtight office, a crowded classroom, or maybe just your own bedroom. Everything seems normal, the temperature's fine, the lights are okay, but slowly, subtly, the energy just drains away. Your thoughts feel like you're wading through lukewarm water. You start blaming yourself. I should have slept more. I need more caffeine. I just lack the willpower to focus right now. That dullness, that inexplicable fatigue, the slight irritability you feel, you assume it's an internal failure. But what if the air itself is changing the way your brain works? What if an invisible chemical, one you produce all the time, is quietly rising around you, altering your entire mental landscape hour after hour? And here's the really surprising part. The culprit isn't the lack of oxygen. That stays pretty much stable. It's carbon dioxide, CO₂, the gas you exhale with every single breath. It is, quite literally, the invisible atmosphere you're thinking in. Hi, and welcome to Brain Binge, the show where we dive way too deep into the weird side of reality. Whether you're trying to fall asleep, stuck on a late-night drive cleaning your room, or just need something interesting in the background, thanks for hanging out with us. Tonight, we're embarking on a deep dive into the air you're thinking in. We are exploring how this fundamental, unavoidable gas slowly changes your focus, your quality of sleep, and even just that feeling you get in a room. This isn't about doom, it's about optimization. We're looking at how small, cumulative chemical shifts can have these massive, tangible effects on comfort and cognition.
It's a really essential topic, because we've become masters of sealing off our environments for energy efficiency, for temperature control, for noise.
Right.
And in doing that, we forget that air isn't just empty space. It's a complex chemical environment. And when you seal yourself off, you create this fascinating feedback loop where the biology inside the room starts reacting to the chemistry it produces.
Okay, let's unpack that chemical environment. Let's start at the most basic level. Everyone knows the name carbon dioxide, but if we break it down, what exactly are we dealing with?
Fundamentally, we're talking about a really small, really stable molecule. It's just one carbon atom bonded to two oxygen atoms. CO₂. It's an extremely common gas, it's non-toxic at normal levels, and it's absolutely foundational to life.
When you say foundational, what do you mean?
Well, carbon is the skeleton of all organic matter, right? It's the framework for carbs, fats, proteins, even our DNA. And carbon dioxide is one of the main ways that carbon travels through Earth systems. It's like a crucial delivery vehicle. It's not just waste, it's a form of traveling carbon that plants can grab right out of the air and turn into life.
And when we talk about measuring these ingredients in the air, we're dealing with concentrations that are so low, they're almost hard to visualize. We use this measure parts per million.
That's right. Parts per million, or ppm, is the only way to talk about it because the concentrations are tiny. It's like the air's tiny print. So for instance, when we talk about the outdoor atmosphere right now, we're hovering around 400 parts per million.
So what does that actually mean, 400 parts per million?
It means if you could grab 1 million molecules of air, and remember, that's mostly nitrogen and oxygen, only about 400 of those would be carbon dioxide. It translates to 0.04%. Just 0.04% of the atmosphere.
That seems negligible. I mean, if it's such a tiny fraction, how can it possibly matter?
It feels negligible, but this is where the incredible sensitivity of biological systems comes into play. We've evolved over millennia to respond to these subtle shifts in atmospheric chemistry. Think of it like a trace element in your diet. You only need a tiny bit, but a small deficiency or excess can have these huge cumulative impacts.
Okay.
So if we talk about a really stale room, let's say 2,000 parts per million, that's still only 0.20% of the air. It's a minute fraction. But the consistent exposure, hour after hour in a closed room, that forces a biological response. That's really the key takeaway.
Yeah.
These are tiny chemical shifts, but the response is very real and very measurable.
That puts the scale into perspective. So now that we know what it is and how we measure it, let's look at where it comes from. We're surrounded by sources, and this is where we kind of move from basic chemistry to the world's constant slow breath.
Yeah, we can basically break the origins of carbon dioxide into 4 main processes. The first and most immediate one is cellular respiration. That's us. It's the process that defines life as we know it. We take in oxygen, we use it to break down food for energy, and the leftover carbon atoms are expelled as carbon dioxide. It's the signature of being alive.
I found the way our bodies transport it really fascinating. It's not just, CO₂ bubbling out of our blood.
Not at all, no. Your body is this incredibly fine-tuned chemical buffer. When CO2 gets into your bloodstream, most of it reacts with water almost instantly to form carbonic acid. That then splits into hydrogen ions and bicarbonate. And that bicarbonate is the main way the carbon travels to the lungs.
And that matters because of acidity, right? The pH level.
Exactly. That chemical dance is essential because those hydrogen ions are what determine your blood's acidity, its pH. So by constantly managing the CO2 level, your body's keeping your blood pH in this incredibly narrow critical range. It makes carbon dioxide an active chemical regulator, not just some passive waste product.
Wow. It's built right into our stability system. Okay, so moving past us as individuals, the second major source is decomposition.
Right. Decomposition is like the microbial breath of the planet. You have microbes, bacteria, fungi. They're constantly breaking down all the organic matter. On the forest floor, in a compost pile, in the soil, they're also respiring, and the output is this slow, steady stream of carbon dioxide. The floor of a forest with all those fallen leaves is one of the biggest natural carbon dioxide generators on the planet.
And then there's the one we're all culturally aware of, the one tied to our infrastructure, combustion.
Combustion is just rapid oxidation. When you burn any carbon-based fuel wood, natural gas on your stove, gasoline in an engine, you're forcing the carbon atoms in that fuel to bind really quickly with oxygen from the air. This releases energy, which we use, and the exhaust gas is carbon dioxide and water vapor.
There's really interesting detail in there about the mass. When you burn carbon, you actually end up with more mass in the gas than you started with in the fuel.
Yeah.
How does that work?
That's a critical point for understanding the sheer scale of emissions. If you burn 1 ton of pure carbon, you end up with about 3.67 tons of carbon dioxide.
Wow.
Yeah, because you've added the mass of the oxygen molecules from the air to oxygen atoms for every 1 carbon atom. It's this massive transfer of mass from the atmosphere into the exhaust, which really highlights the scale of what happens when we burn fossil fuels globally.
And the fourth source, which brings us right back to biology and gives us a perfect analogy for a sealed room, fermentation, the backup generator mode.
Fermentation is beautiful. It's basically life running when oxygen isn't available. Microbes like yeast that convert sugar into ethanol, and crucially for our discussion, carbon dioxide gas. It's a process that happens everywhere.
And we see it every time someone bakes bread.
Absolutely. The rising dough isn't magic, it's just physics powered by biology. The yeast is eating the sugars in the flour and releasing CO2. That gas gets trapped in the stretchy gluten network of the dough. As the yeast produces more gas, the bubbles expand and the dough inflates.
And the sealed container lesson from brewing takes this and applies physics to it, kind of modeling the ocean.
Yes. In brewing, if you seal the fermenting liquid, that CO2 gas has nowhere to go, so it dissolves into the liquid under pressure. That creates carbonation, the fizz. And that demonstrates 2 key principles. Pressure and temperature control how much gas dissolves into a liquid. A brewery tank is like a perfect little miniature model of gas-liquid exchange.
So if we take that lesson back to our initial scenario, that crowded office or classroom, the description starts to make a lot of sense. A room full of people is basically a slow fermentation chamber.
Minus the yeast, plus the nervous systems.
Right.
It's a pretty good comparison, actually. It just grounds the fact that the carbon dioxide rising in a room isn't some exotic pollution. It's the natural, inevitable output of human life. It's just what happens when you put constant generators into a box with not enough air exchange.
Okay, so let's take the ultimate zoom out beyond our little rooms to the ultimate buffer that keeps planetary CO2 in check over huge timescales. The ocean. If our body has a buffer, the planet has this giant carbon bank.
The ocean is by far the most significant long-term storage sink for carbon on Earth. Without its ability to absorb CO2, atmospheric levels would be dramatically higher. You can think of it like a massive buffer with different layers that work on different timescales.
And what are those layers?
Well, you have the surface ocean, which is the part that's directly touching the atmosphere. That's the fast account. It's exchanging CO2 over days, months, always trying to reach equilibrium with the air. And then you have the deep ocean. That's the slow storage layer. Because of the slow circulation of the planet's oceans, water down there can hold carbon for decades, centuries, even millennia before it comes back up.
And the physics are the same as the brewery tank. More CO2 in the air means more dissolves into the water.
Precisely. And temperature is huge. Just like a cold soda holds its fizz better than a warm one, the cold polar oceans are critical. To sinks, because cold water can hold way more dissolved gas than warm water. It's why even small changes in ocean temperature can really affect the planet's ability to buffer all this.
But the ocean doesn't just hold on to the CO₂ gas, right? It does this shape-shifting trick, converting it.
It does, and that's the key to its effectiveness. Once carbon dioxide dissolves into seawater, it rapidly converts into bicarbonate and carbonate. This conversion is crucial because if the carbon just stayed as CO₂ gas, the surface water would get saturated really fast and absorption would just stop.
Oh, okay.
But by converting it, the ocean is basically hiding the carbon in these different chemical costumes, which allows it to store these vast quantities without running out of space.
So it's chemically managing the load, kind of like our blood does, just on a planetary scale.
It's the exact same chemical principle, just much slower. And life itself actually helps this process along through what's called the biological pump.
Tell us about the biological pump. And marine snow, that sounds pretty descriptive.
The biological pump is this process where tiny plant-like organisms at the surface phytoplankton, they use the dissolved carbon dioxide to grow. They form these little calcium carbonate shells or just soft tissue. And when they die, or when they're eaten and excreted, they fall slowly toward the seafloor as these little carbon-rich particles.
And that's the marine snow.
That's the marine snow. And this process is vital because it physically transports carbon from the surface layers, which are in contact with the atmosphere, down into the deep ocean storage layer. It effectively locks it away from the atmosphere for a very long time.
So the deep ocean is like this ultra-slow conveyor belt.
Exactly. But it's not a one-way trip. Through ocean circulation, this deep carbon-rich water eventually comes back to the surface. It's a process called upwelling. And when that old, cold, carbon-rich water surfaces, depending on the pressure and temperature, it can release some of that stored CO₂ back into the atmosphere.
This really highlights the enormous difference in timescales. The atmosphere is a fast room, your bedroom is a slightly less fast room, and the deep ocean is just glacial.
That's a perfect way to put it. Changes we make today don't just affect the air right now. They commit the deep ocean to decades or centuries of adjustment. And that's not even getting into the really slow geological timescales, volcanoes and rock weathering that operate over millions of years. They're all connected, but they move at wildly different speeds.
Okay, let's bring it all the way back down to our personal immediate environment, the room we're sitting in right now. We know the planet's baseline is about 400 to 430 parts per million outdoors. That outdoor air is our starting point for everything indoors.
Right, and that baseline, it even has seasons. The whole atmosphere breathes. In the northern hemisphere, where most of the land is, the forests and crops draw down huge amounts of carbon dioxide during the spring and summer.
Through photosynthesis.
And it causes the global concentration to dip slightly. Then in the fall, when the plants go dormant, the concentration rises again. It's this beautiful, reliable sawtooth pattern every year.
Okay, so now we introduce the sealed box effect. How does indoor carbon dioxide manage to climb so quickly from that relatively low outdoor baseline?
It's a simple math problem, really. It's determined by three things: the number of CO₂ sources, which is almost always people, the volume of the room, and the ventilation rate. That is, how fast fresh air is replacing the stale air. Since we're constant generators of CO₂, putting us in a tight box just guarantees the concentration will rise, and often it rises pretty steeply.
And the bedroom, for a lot of listeners, that's probably the most important place to look at because we spend 8 continuous hours there. Door closed, windows closed.
The bedroom is the perfect stage for the world's slowest overnight carbon dioxide experiment. You have a small volume, a continuous source, 1 or 2 sleepers for a long time. It is extremely common for CO₂ levels in a normal, unventilated bedroom to cross 1,000 parts per million and often hit 1,500 or even higher by morning.
So what are we looking at for typical ranges?
A well-ventilated home or a modern office should probably stay in the 600 to 1,000 parts per million range. That's considered pretty acceptable. But you can see levels skyrocket to 1,200, 1,800, even 2,500 parts per million in crowded places. Small meeting rooms, old classrooms, theaters, places with poor HVAC. Those are the environments where we see the performance issues really documented.
Before we get to the biological effects, we have to address a couple of myths. First, this idea that since carbon dioxide is heavier than air, it pools on the floor in some deadly layer.
Right. It's true that the molecule itself is heavier than nitrogen or oxygen molecules, but the idea that it forms this static, deadly layer on the floor in a normal room, it's not accurate. Indoor air is constantly being mixed. You have convection currents from our body heat, from electronics. You have airflow from HVAC systems, tiny drafts under doors, people moving around. All these things turn most indoor spaces into slow, constant blenders. The gas gets distributed pretty evenly. Gas stratification is only a concern in, very specific industrial safety scenarios like deep pits, not your living room.
Okay, that's a clear distinction. And the second, more common myth is that the stuffy feeling comes from running out of oxygen.
This is the biggest one. People assume that feeling of sluggishness is hypoxia low oxygen. But the amount of oxygen in the air is so massive and our metabolism at rest is so slow that oxygen levels almost never drop in any meaningful way. You might go from 20.9% oxygen down to 20.8%. That change is physiologically irrelevant.
So if it's not low oxygen, what is the stuffy feeling?
The stuffy sensation is a cumulative effect. It's the rising carbon dioxide itself, but it's happening at the same time as rising heat, rising humidity from our breath, accumulating body odors, and rising concentrations of VOCs, volatile organic compounds, that are off-gassing from furniture and electronics.
So the room isn't running out of the good stuff?
No, it's just becoming saturated with the byproducts of us being in it. Most rooms don't run out of oxygen. They run out of freshness, and carbon dioxide is the perfect quantifiable indicator of that lack of freshness.
Now we get to the core question. What does this rising CO₂ actually do to our brain? We've already established that it's a critical regulator in the body.
Yeah, it's more than just waste. It's a vital signaling molecule. The body uses the pressure of CO₂ in the blood to help set your breathing rate and manage that critical blood pH. Your urge to breathe is intrinsically linked to how much CO₂ you need to get rid of.
And the way we detect it is pretty sophisticated.
It is. We have these highly sensitive chemical sensors, chemoreceptors, mainly in the brainstem, and they don't monitor CO₂ directly. They monitor the slight change in acidity, the pH drop that happens when CO₂ forms carbonic acid in the blood. When CO₂ rises, acidity increases, and that immediately tells your body to breathe faster and deeper to offload the excess.
And what's surprising to a lot of people is that our bodies are usually more sensitive to that rising CO₂ signal than to low oxygen.
Absolutely. Unless you're at an extreme altitude or something, your breathing rate is governed by the need to expel CO₂, not the need to inhale oxygen.
Yeah.
And that's why we feel those subtle symptoms at these modest indoor elevations, even with stable oxygen. The body is in this low-grade, constant fight to keep its chemistry balanced.
So in that stuffy room range, the 1,000 to 1,500 parts per million we talked about, what are the everyday symptoms someone should be looking out for?
The symptoms are insidious because they're subtle, and they're so easy to blame on other things like stress or fatigue. The most common reports are increased sleepiness, that pervasive brain fog that makes it hard to concentrate, and just a reduced sense of air quality. Some people report mild tension-type headaches and a subtle increase in irritability, just a low-level stress tone because the nervous system is running a little bit hotter.
So, to frame it again, the CO₂ doesn't have to reach dangerous levels to knock you out. It just has to introduce this subtle, constant physiological load that tilts your nervous system a few degrees off center.
That's the critical insight. It's an environmental handicap. Your body is always just slightly stressed, working a little bit harder than it needs to, and that burden shows up in how you feel and how you think.
And that leads us directly to cognition. Studies have shown pretty consistently that higher indoor carbon dioxide correlates with worse performance, especially on complex tasks.
This is where the cost of poor ventilation becomes measurable. Research, especially in that 1,000 to 2,000 parts per million range, shows that the functions that get hit the hardest are our executive functions. Decision-making quality, strategic thinking, the ability to use information effectively, and crucially, sustain concentration. Simple, repetitive tasks are often fine, but the high-level, expensive mental work degrades.
Why do those complex tasks fail first?
Because complex cognition, abstract reasoning, detailed planning is metabolically really demanding. It requires huge resources in the prefrontal cortex.
Yeah.
If your body is fighting this low-grade load from rising CO₂, or if the environment is just making you sleepy, the brain responds by basically entering a power-saving mode.
Wow.
You can still do basic operations, but the patience, the clarity, the sustained effort required for high-performance thinking, those are the first resources to get rationed away. It's a subtle shift from high-efficiency processing to just low-effort maintenance.
It's like the brain says, we're going to conserve resources here, We don't have the luxury for optimal performance right now.
Precisely, and this is where we have to get into the nuance. CO₂ is not always the only villain. It's both an active ingredient and a really reliable clue.
Okay, let's clarify that distinction between cause and proxy.
In strict lab conditions, high CO₂ by itself has been shown to physiologically impair performance, so it is an ingredient. But in the real world, it is also a highly reliable proxy for low ventilation. If your CO₂ levels are high, it means your air exchange rate is low. And if the air exchange rate is low, it means every other indoor pollutant, odors, VOCs, humidity is also accumulating at the same time.
So a high CO₂ reading is a perfect diagnostic tool.
Yeah.
Even if the CO₂ itself isn't the only thing giving you a headache, it's a guarantee you're breathing a concentrated mix of everything stale in that room.
That is the critical takeaway. Carbon dioxide is both an ingredient and a clue. Sometimes it's the direct cause, often it's just a reliable, measurable sign that the room isn't breathing and you're getting the whole stale air package.
Let's focus this now on the bedroom. This is where we spend a third of our lives, and like we said, it's an overnight CO₂ experiment.
Sleep is. It's a non-negotiable process of restoration. It requires stability. And when ventilation is poor, the rising carbon dioxide attacks that stability by adding this subtle physiological load that your body has to deal with, even while you're asleep.
You get that full human signature building up in the air.
Absolutely. Over 8 hours, the room gets warmer, the humidity spikes from your breath, and odors accumulate. And studies have found a really consistent correlation. People who sleep in poorly ventilated rooms, even if they sleep for the same amount of time, they rate their sleep as significantly less refreshing.
So what's happening when that CO₂ load is constant all night?
Well, the data is complex, but there's evidence suggesting that sustained high CO₂ can impact sleep architecture. It might reduce the time you spend in deep restorative sleep, or it could subtly elevate your autonomic stress response. The result, either way, is increased next-day sleepiness, reduced alertness, and that feeling of waking up already tired.
I think this is where it really hits home for people. Have you ever blamed willpower for a foggy day when it was actually just the room? We're so quick to assume it's an internal failure when the environment is the limiting factor.
It's the easiest mistake to make. If you're dragging yourself through the morning, you blame the 8 hours you got. But often, the issue wasn't the quantity of sleep. It was the quality of the air you were breathing. You were forcing your body to compensate for an increasingly stale environment for that whole restorative period.
That brings us to that memorable line. Sometimes you didn't sleep badly, you slept in yesterday's air.
It perfectly captures the problem. You're trapped with the results of your own metabolism.
Okay, let's switch from personal wellness to shared spaces. Carbon dioxide is starting to be recognized as a quiet proxy for assessing potential infection risk. And we have to be really clear here. And see, O2 is not a virus.
Correct. It's not the contaminant, but it is a crucial mechanical gauge. When people share a space, they're exhaling CO₂ and potentially aerosolized droplets that can carry illness. If your CO₂ monitor reads high, say 1,500 parts per million, it means the fresh air is not coming in very fast. And that means a much higher percentage of the air you're inhaling is rebreathed air that was just in someone else's lungs.
So it's a metric for density and air exchange.
Precisely. High CO₂ means poor ventilation, which means less dilution of any potential airborne contaminants. It becomes this essential tool for optimizing indoor spaces, schools, public transit, offices to minimize sharing airborne aerosols. It's a tool for measuring airflow, not a verdict on what's in the air.
And this leads right into the critical confusion people have when they try to fix their air quality. The difference between ventilation and filtration. They're completely different tools.
This is maybe the most important practical takeaway. If you're going to try to improve your air, you have to know the difference. Filtration, especially with a HEPA filter, is designed to remove particles.
Things like dust, pollen, smoke.
Exactly. Dust, pollen, pet dander, smoke particulates, and aerosolized droplets that might carry viruses. A HEPA filter works by physically trapping these particles. But, and this is the critical point, a HEPA filter does not remove carbon dioxide.
And that's because of the physics, right? A particle versus a gas.
Exactly. Carbon dioxide is a single gas molecule. It's way too small to be trapped by the physical mesh of a HEPA filter. To remove CO₂ gas, you need specialized chemical scrubbers, which are, not part of consumer air purifiers.
So for the listener, the simple translation is, if my room feels stuffy or my brain feels foggy or my CO₂ monitor is high, the answer isn't a bigger filter. The answer is ventilation.
That is the rule of thumb.
Yeah.
If the problem is stuffiness and high CO₂, you need ventilation. You need to exchange stale indoor air with fresh outdoor air. If the problem is smoke or pollen, filtration helps a lot. They're both useful, but they solve totally separate problems. A filter can clean the air, but it can't replace the air.
So if we accept that carbon dioxide is this perfect gauge, we need a way to turn the invisible into a number. And this is where CO₂ monitors come in, and they really do change your behavior.
They provide instant objective feedback. Before you have a monitor, it's all subjective. It feels stuffy in here. No, it doesn't. After you have one, that feeling is validated or refuted by a number. It turns this abstract feeling into a tunable parameter.
So how do these little devices work? There's some pretty cool physics in every monitor.
Yeah, they mostly use what's called an NDIR sensor non-dispersive infrared sensing. The physics is really elegant. Every CO₂ molecule absorbs infrared light at a very specific wavelength. The sensor has a little infrared light bulb, a chamber, and a detector. It shines the light through the air and measures how much of that light makes it to the other side.
So the more CO₂ there is, the less light gets through. It's measuring a shadow away.
Exactly. It's measuring the absence of light to calculate the presence of the gas. It's a highly reliable way to do it. And this brings us back to that connection we teased earlier. The physics that makes the NDIR sensor in your room work is the same fundamental physics that drives the greenhouse effect globally.
That's a beautiful symmetry. The way the molecule affects your brain is its chemistry with water. But the way we measure it and the way it affects the planet is all about its ability to trap infrared radiation.
It's the same molecule doing two entirely different things on two different scales based on the same principle of infrared light absorption.
So if a listener gets one of these devices, how should they interpret the numbers? We should probably give some loose guidelines.
Yeah, and it's important to remember that individual sensitivity varies, but we can define some helpful bands. The very fresh range is about 400 to 600 parts per million. That's basically outdoor air. You'll probably only see that right after you've opened a window. The common, pretty good indoor range is generally 600 to 1,000 parts per million. Most modern HVAC systems are designed to keep a room below 1,000. When you cross 1,000 and head up to 1,500 parts per million, that's when the room is noticeably underventilated. And that's where you start to see consistent reports of fogginess, reduced comfort, maybe mild headaches. And once you get past 1,500 toward 2,500, the air is quite stale. That's where most studies document significant performance complaints.
People should know about the quirks of these monitors, too. Why do they sometimes seem to drift?
Right. Most consumer monitors have a feature called automatic baseline correction. It assumes that at some point every week, the lowest reading it sees must be the outdoor air level, so it resets its own baseline to 400 parts per million. This works great if you open a window now and then, but if you leave it in a sealed room for months, the baseline starts to creep up, and it'll start giving you inaccurately low readings.
So the device, just like the room, needs to breathe fresh air once in a while to stay calibrated.
A perfect analogy. And placement matters. Don't put it right next to your face, and don't put it right in front of a vent. Mid-room at breathing height is usually the best spot to get a good average reading.
Okay, now for the most empowering part.
Yeah.
Practical, simple ways to fix this. If the master solution is exchanging indoor air with outdoor air, what are the easiest, highest payoff actions?
The simplest and fastest is what we call the air flush. You just temporarily accept a small temperature change for a major air quality gain. Open a window wide for 5 to 10 minutes, even if it's cold. That can dramatically reset your indoor CO₂ from, say, 1,500 down toward 500 really quickly.
And if you can get cross-ventilation going, it's even faster.
Exponentially faster. If you can open 2 windows on opposite sides of the room or a window and a door, you create a cross breeze. That flow exchanges the air way faster than a single opening.
We should also be using the fans we already have in our homes.
Strategically, yes. Your kitchen and bathroom exhaust fans are designed to pull air out of the room. This creates negative pressure that then passively draws fresh air in from elsewhere, under doors, through vents. Using those fans can really help increase the ventilation rate.
I thought the distinction between a long, small crack and a short, decisive flush was really interesting.
It's counterintuitive. Leaving a window cracked just a tiny bit all day might not result in much air exchange at all. But a short, decisive 5-minute air flush actively purges the entire volume of stale air. It often provides a much greater overall benefit.
And for the bedroom, which is the highest payoff for health and performance.
The highest leverage things you can do are ventilate the room thoroughly before you go to bed to lower the starting point, and then again first thing in the morning to clear out everything that built up. And if it's safe and comfortable, even cracking a window a tiny bit overnight can make a profound difference in keeping those levels from spiking. And remember, don't confuse cold air with fresh air. You can ventilate briefly without freezing the room just to get that chemical reset.
And for those of us working or studying, we can use this as a performance tool, right?
Yeah.
Make it a habit.
Absolutely. When that mid-afternoon slump hits, treat that fogginess as a diagnostic moment. Instead of just reaching for more coffee, try an air check before coffee. If the monitor is high, step outside or do a quick 2-minute air flush of your room. It can provide this genuine physiological reset that's often more effective than caffeine alone. Just schedule little air breaks the way you'd schedule water breaks.
Okay, let's zoom out one last time, connecting the local chemistry that affects our breath to the global physics that affects the climate.
The connection is really powerful because it's the same ingredient. The carbon dioxide molecule that makes your meeting room feel stale is the same molecule, using the same infrared physics that's a key part of Earth's atmosphere. It's the chemistry of constraint.
But the framing here is crucial. The dynamics of a room are about comfort, performance, immediate saturation.
Yes, the scale is vastly different. The issue globally is the rate and scale of all the additional carbon dioxide being released rapidly from fossil carbon that was stored underground for millions of years. This rapid release strengthens the natural greenhouse effect, driving long-term warming and other large-scale changes.
So in essence, the physics that makes your bedroom air stale is like a perfect miniature accelerated model of the much slower physics shaping the whole planet.
Exactly. The atmosphere is the global room. Your ventilation manages the local room. Both are governed by invisible chemistry and feedback loops. Understanding why your air feels stale is understanding a tiny, manageable piece of the larger planetary system.
This has been a true deep dive. We started with that subtle feeling of dullness and fatigue that we almost always blame on ourselves, a lack of effort, a lack of rest. And now we can see that this invisible air chemistry is quietly, constantly shaping our mood, our focus, and the quality of our sleep.
And that understanding is so empowering. This isn't about fear, it's about optimization. It's about control. Because once you can see this invisible system, either with a monitor or just by recognizing the signs, small, deliberate changes in habit, that 5-minute air flush can make a tangible difference in how you think and how you feel.
I think the most provocative question we can leave you with, something to mull over, is this. When you look back at your last few weeks, how much of your day-to-day brain fog, how much of that sleep hangover or that energy crash you felt was actually a failure of architecture and poor ventilation, and how much was truly a failure of willpower?
Once you start measuring and managing your environment, you might just find you get back the clarity you thought you'd lost.
Thanks for listening to Brain Binge. We've been deep diving into the air you're thinking in. If you enjoyed this deep dive, please like, share, and subscribe, and let us know what you'd like us to cover next. Until next time, stay curious, stay safe, and have a blessed day.